just give perturbations to a few of them. The perturbations that we give are exactly the same, and they will move the phase from this initial phase phi I, the current instantaneous phase of the oscillators, to some phase phi p. And of course, the choice of which oscillators to perturb is something that it's up to us. So what we see over here are different sorts of figures that are obtained by different choices of which node that we decide to perturb. And you can see that you get a whole different range of outcomes. And the colors basically correspond to the kind of state you end up with. Blue means exact sync, which means you just go back to exact synchronization. And all the different colors are these different kinds of states that you see over here. I won't go into the details, but basically the point is that. The point is you can get different types of states. We studied, and there were some interesting results that which relates to the kind of topological sort of behavior of these parameter space diagrams depending on the perturbation sequence. But I'll leave that for maybe another time. But so having been able to sort of systematically do this, we said, all right, so now let's try and take a ring, and now we just perturb two sides. We move one side to some phase phi p1, one side to phase phi p2, and then we see what are the different kind of patterns. And again, the different sort of panels correspond to different choices in terms of the nodes that I should say how far apart the two nodes that we perturb are. And once again, we get the different types of patterns. But now we start, okay, so since we have effectively two inputs, basically this node over here and this node over here, we can effectively threshold the input. So we can say that if the input phi p1 and phi p2 are less than some value, we can say that the input is, we can say that it's off, you could say, and if it's above a threshold, you can say it's on. Similarly, we can also say that if it goes back to exact synchronization, we can say that the output is off, and if it does something else, we can say it's on. So in that way, we can talk about the inputs and the outputs in terms of off and on. And you can, once you do that, it turns out that you can actually look at some of these potentially as gates. So for example, over here in this panel G, if the input phi p1 and phi p2 are on, which is that they're above a threshold, you can say this threshold, then you go back to exact synchronization. But elsewhere, you don't. Elsewhere, you get to some pattern. Now this is, you can think of it very, very roughly as a NAND gate. Basically, only if both are on, you get an output of 0. Otherwise, you get an output of 1. Of course, now the problem with this, of course, is in terms of implementation. And so we thought that although this is interesting and quite promising, this potentially could be challenging to try to do an experiments. So then we asked, is there another way that we can try to come up with a sort of a way of looking at these sorts of systems in terms of logic gates? And so with this, we now return to spot. So the spot is something which, as I said, it's very simple in a way, because effectively it either goes to a high state or goes to a low state. And so it's very easy to think of this as a binary string. However, now in principle, each you can have, like I said, you could have potentially, if you have n oscillators, you can have potentially 2 power n spots, but that's not the case. It actually turns out that there's a severe constraint on the number of spots that you can get, and this is because if you have, let's say, 3 consecutive zeros or 3 consecutive 1s, that means that the node in the center effectively has very low or almost negligible diffusion between its neighbors, which means that effectively it's uncoupled. And if that's the case, it's going to start oscillating again, because it had only stopped oscillating because of the coupling. So effectively, if it feels no coupling, it's going to start oscillating again. So that's why you can't have, you can potentially get around it by really cranking up the diffusion, but for most reasonable values of diffusion, it's not something that you can obtain. And in fact, although I won't get into this here, you can actually, there's some sort of nice combinatorial arguments and other types of arguments to work out exactly the number of spots that you can obtain.
I understand this. So you were saying if you have a chain of 10 oscillators, you cannot have global oscillation depth in all 10 of them.
Not in this parameter regime, no. Because
in your spatio-temporal time series, yeah, there are places you did.
Yeah, no, because in this particular regime that we're in, like in this.
What's the difference? I missed that. I'm sorry. I just missed
Yeah.
that. Because if you look at your spot over there,
Yes.
It was not limited to 10, right? I mean, you could have larger domains of fixed point dynamics. That's spot, right? You're calling fixed point dynamics as spot.
Well, basically temporally invariant. So basically all the nodes are temporally invariant.
So fixed point.
Yeah.
I mean,
So
I don't understand the restriction that you cannot have more than X amount of coupled oscillators at fixed points. Maybe at your parameter, but it's not very generic, you realize that?
yes. Okay, sure. Yeah. So basically, so one can sort of can work out these number of spots, and now these spots, like for the case of a ring, so as I said, you can for this particular figure that I've shown over here, this is for the case of a chain containing 10 oscillators. So here it turns out you have around 68, you have exactly 68 spots. But for a ring, it turns out you have, for the same size, you have only 14 spots. And what we show here is the number of times that you obtain a given spot starting from random initial conditions. And so we see here that this particular spot, which is simply like a 0, 1, 0, 1, 0, 1, this is something that you are much more likely to see than any of the other spots. There's actually an argument for this which will come in one of the later slides. So anyhow, so now that we see that these are the kind of spots that we can obtain. What in principle we can do is that, so the spots they all coexist. So in other words, for a given regional parameter space, you can have multiple spots, right? So you can provide a perturbation to one spot to obtain another spot. So like for example, a spot like this, you can provide a perturbation, you get another spot. The perturbation itself can be thought of as a binary string, because you can decide, am I going to perturb a site or not perturb a site, right? So each site I decide, am I going to perturb it or not perturb it. So I have an input string with binary perturbation, binary output, also binary. And so you can think of this effectively as a computation that generates an output binary string from an input one. Okay. The perturbation is applied as follows. All we do is that in the inhibitory variable, we just give a transiently applied perturbation of a fixed amplitude, and it's either 0, either we don't perturb it, or we give it a fixed amplitude. And then, so in this example we see over here, we apply a perturbation for a very, very short duration, and this is the output that we obtain, right? So we go from this particular spot state to another spot state. And this is something which we thought that potentially it could be implementable in light-sensitive chemical systems, where as you increase the intensity of incident light at a particular site, that could lead to a higher level of inhibition. So maybe this is something that could be done in practice as well. So now, one thing that, so if we know all the spots that we can obtain, we can provide perturbations to the spots, so it can be perturbed potentially in 2 power n minus 1 ways. And so we perturb them and we see what spot do we end up in, right? So you can go from one spot to another spot, and we can look at the probability of reaching a given spot state via perturbations to the other states. That's one thing we can measure. That's p-pert. And we can also, through a simple linear stability analysis, we can calculate the largest eigenvalue of the Jacobian. And then when we compare them, what we observe is that the sites with the higher p-pert have the most negative lambda max, which means that these particular sort of sink sites, they're associated with higher local stability. But if you notice one thing, these are not the same as this, what you see over here. So here, these sites are, like for example, this is 0, 1, 0, 1, 0, 1, which is not what we see over here. So that is something which you can obtain when you look at the global stability. So here, this is a site with the largest basin size, and this is something that in order to understand this, we looked at a particular, we came up with sort of an energy function that describes the energy of a site in terms of a spin. So we basically assign a +1, -1 for high-low states, and we obtain the energy function through this simple sort of formula. And it turns out that this particular site is associated with the lowest energy. So the global and local stabilities are obviously quite different for the different types of spots, and there is a relation between the numbers of zeros and which I probably won't get into right now. Okay, so this is the last slide. So basically, so now that we understand that, we can provide perturbations to all the different spots, and we can see like how the kinds of transitions that can occur. And we find that nodes with like four zeros, they typically flow towards nodes with 5 or 6 zeros, and so you don't get flows backward. So there's sort of a kind of a logic in terms of how perturbations take you from some sites to other sites. So the nodes with four, so basically that's all I need to say about this. So okay, so in summary, we can get diverse spatial temporal patterns from these sorts of systems, which can be viewed as a form of computation. And then we've basically been able to implement a kind of NAND logic using one of these types of patterns, which is this phase defect. The nature of the spot itself, it allows for like a very nice interpretation in terms of binary strings, and we have like a very clear idea regarding like the rules that govern all the various transitions between the spots, and this potentially could give kind of a guiding principle for a way to implement computational logic on these types of states. So so with that, I'll just mention so these are the works that are relevant to this talk. The latest one is on archive. That's it. Thank you. HTML.
Okay, it's okay, I prefer this. First up, I'd like to thank the organizer, who also happens to be my mentor, Shitabra, for giving me this opportunity. And also, I have to say that it's a privilege to be giving a talk in a meeting like this, commemorating achievements of a senior professor. Very grateful for that too. All right, so today I'll be talking to you about the role of mechanics in excitable media. This is a work that we've recently finished and in the process of writing it up. All right, so Shakti has briefly covered what an excitable media is, but briefly. So what is a biological excitable media? So you take a cell from an excitable tissue, you apply current stimulus, the response of the cells looks like this, where on the vertical axis I have the potential inside the cell, on the horizontal axis it's time. So there's a sharp rise in the potential of the cell and slow relaxation to its normal state again. So, and this event is called an action potential. So cells which can exhibit an action potential are excitable cells, and the tissue that they constitute are called excitable tissue. Right, so here's a list of some excitable tissues that are found in a human body. It's not an exhaustive list, but yeah. So some of the excitable organs that are found in our body, they require muscle contraction to perform their biological function. So here I give you 3 such organs: the heart, uterus, and the gastrointestinal tract. So these 3 organs, they need to contract. So in the case of a heart, to pump blood, uterus to give birth, and GI tract to move food in our colon. Now, these organs require a certain degree of muscle contraction to perform their respective functions normally. So, for example, in the case of heart, if the contractions is not synchronous or not coordinated, then the blood might not be pumped efficiently, and that could be lethal. Similar complications can arise in the other 2 systems. Now, it is known that the contractile activity in these excitable media are mediated by electrical activity, which means you have excitation first, which means this action potential, then that induces cellular contraction or muscle contraction. So people mostly focus on the excitable and in the electrical dynamics, sort of thinking that, okay, the mechanical activity is just sort of slave to the electrical activity. But it is known that there is a feedback from the contractile activity to the electrical activity. And this mechanical feedback could play crucial role in the dynamics of both electrical as well as mechanical activities. So today I'll just briefly discuss that. All right, so again, this is the Shizunaguma model. Shakti has again briefly discussed this. This is just to show that this is a 2-variable model. V here mimics the potential inside a cell. You can tune the parameters in such a way that it is oscillatory or non-oscillatory. Oscillatory cells, we'll call it oscillators, and the non-oscillatory cell, I'll call it an excitable cell. All right, so before we include mechanics in our model, let's see what are the various spatiotemporal patterns one can see just with diffusive coupling between the cells. So I take a heterogeneous media composed of oscillators and excitable cells, and we take such heterogeneous media because most of the excitable media that are found, that I sort of showed you in the introduction, they are heterogeneous. It's always a mix of oscillators and excitable cells. And the density of these relative cell types, let's say oscillators, it can change in due time because of natural process like aging or because of diseases, right? And also the diffusive coupling between the cells, that can also change in the course of time, again because of natural process or disease. Right, so we take this setup and see what sort of spatial temporal patterns emerge in the system. So the top row panels here show the patterns, but let me just play a video. I think that will explain better. I hope it, all right. Okay, so I'll explain it to you at what parameter regions we see these various patterns, but for now, let's just look at the patterns. So the first one here, CO as in clustered oscillation. The oscillations are spatially localized, they're clustered. And then there you see traveling waves, TW as in traveling waves. Then you see, where the local regions are sort of synchronized, and you see a phase where the whole system sort of oscillating in phase. We call that as a coherent phase. So okay, so these are the various patterns that we see. Let me just play once again. Just right. So where do we observe these patterns? So again, the parameters that we are controlling are the density of cells and diffusive coupling. So here, rho, density of oscillators, and D, the diffusion constant. So
the boundary conditions are no flux?
Periodic boundary condition.
Periodic.
Yeah. So CO, the clustered oscillation is observed when the coupling between the cells is low. right? And it makes sense because if the density of oscillators, again, and also the density of oscillators is also relatively low. So you have oscillators sort of sprinkled in the medium, and because of the low diffusive coupling, the excitation cannot propagate in the medium, so you have a clustered oscillation. You increase the diffusive coupling between the cells, and then the excitation can now propagate from these clusters throughout the medium. So you see bands of excitation waves propagating in the medium. You further increase the oscillator density. Now the cluster sort of expands because you have more oscillators, right? And then the coupling is also stronger because you've jacked up the diffusion constant. So you see more synchronized oscillation, and we call that as locally synchronized. You further increase oscillator density, then all of the medium now sort of oscillate in phase, and you go to the coherent state. Now these are the order parameters. So just to characterize these various phases or dynamical states, we define order parameters to sort of characterize dynamical states. Also, we see other phases here, but let me not go into the details of this in the interest of time. But if you have questions, I'd be happy to answer them later.
I'm still wondering, why would you use periodic boundary conditions?
This is just to ignore boundary effects. You can also do this with no flux.
When you do the heart and all that,
Right.
no flux, right?
It's no flux. So even though you do no flux, the results will still hold. I also have done some
The phase diagram will remain
right.
the same?
Qualitatively, yes, it might change. And also I use periodic boundary because of the numerical method that I was using, sort of a pseudospectral method. All right, so that was without mechanics in the model. Now we introduce mechanics, again, without going into the details of these equations. Let me just tell you that we use linear elastic model of a damped. Okay, so U here is the displacement field. Sigma is the stress tensor. It has two components, passive as well as active, because we have excitations. And so the basic idea is this. Let's say in a square lattice you have cells. You excite the middle cell. The middle cell sort of contracts, indicated by red color here. That then stretches its neighboring cells. Right? Now, because of this stretch, certain ion channels, protein ion channels, gets sort of activated by that. They open up. So when they open up, ions can rush inside the cell, and that sort of promotes excitation. All right. So that's what we try to incorporate in the model. Okay. Now, mechanics does two things. So as this cell contracts, as I said, it activates ISAC, and also now, because of mechanics, you can sort of understand that cells further away from its nearest neighbor can sort of sense, right? Because if a cell contracts, it'll stretch its neighboring cells, and depending on the stiffness of the matrix or the medium, there will be sort of long-range interaction. So it can be shown that this sort of power law, 1 over R being the distance between the cells. Okay.
So I'm sorry, I'm very curious about this. So your conclusion, or something that it actually is a positive feedback to the eye. Is it based on experimental data?
Right. So these stretch activate channels are found, yeah. Right. So again, activation of ISAC in the neighboring cells can be thought of as increasing the coupling strength. Also, mechanics introduces long-range interaction. So without mechanics, the interaction is just nearest neighbor, right? Because of diffusive coupling. So mechanics does two. So because of those two effects, you can already sort of sense that it will promote synchronization in the medium. And indeed, we do see synchronization. So these are the two phase diagrams without mechanics and with mechanics. So if you look at the coherent state, you see that this region has sort of expanded. So we see synchronization in a much more, region now. And also these oscillatory states have sort of, so these are the quiescent states where the medium does not, there is no activity in the medium because of the low density of oscillators. So that is sort of, so the other regions have sort of expanded at the expense of this quiescent state. So it promotes oscillation and also synchronization. Now, lastly, I would like to end by saying that mechanics can also sort of promote synchronization in media where the diffusive coupling between the cells can be low. So, for example, in the heart, the sinoatrial node, the pacemaker of the heart. So I'll just draw a cartoon here. So the sinoatrial node locates somewhere here in the right atria, and these being the 4 chambers. So in the sinoatrial node, it is seen experimentally that the proteins forming the gap junctional coupling sort of decreases, the expression level decreases from the periphery to the center. So there's a gradient in the diffusion constant, right? So in such scenario, the question is, how does sinusoidal node, how is it able to still excite in phase, or is still able to oscillate in synchrony? So we sort of think that mechanics could be playing a dominant role there. So even though there is low diffusive coupling, because of mechanics, it can activate the ISAC, stretch activity current, and that can promote synchronization. So these two sort of column of panels here, again, time. So this left region is without mechanics. So the diffusion constant sort of decreases from periphery to the center, okay? So you can see that the excitations here is sort of fractionated, it's uneven, right, because of low diffusive coupling. But if you include mechanics, now this excitation becomes much more sort of synchronized, right? So this is what we think that might be happening in the case of sinusoidal node, although this has to be sort of tested. Right, so I think I went pretty fast. So in conclusion, we see that without even mechanics, various sort of spatiotemporal patterns can emerge in an excitable medium with oscillators and excitable cells. And we show that the mechanics can enhance synchronization, and it could be the primary source of synchronization in regions where the diffusive coupling is low. Right, so okay, that's in brief what I wanted to discuss.
Questions?
Yeah.
So when you had this oscillator density, so it was randomly distributed,
Randomly
right?
distributed.
So suppose you actually had some sort of pattern, like stacked in a row, the same density, do you expect it to make walls or some? Do you think?
Walls. Okay,
there might be some.
Like a pacemaker sort of.
Well, Shitabra was such an expert with those scar tissue things in various places, right? I mean, so I'm saying, suppose you had this.
Non-conducting.
I mean, suppose you put it in a spatial.
You had some speculations about what non-conducting areas would do, right?
But okay, I'm not able to. So I mean, what's the question though?
So, well, there are two. One, of course, is a more straightforward one where you had this density which you sort of put randomly, right?
Right.
So suppose instead of that, if the oscillator, say the same number, say half and half was put like all in one part, and is there any change in your phase diagram?
Sure. Again, okay.
So I mean, I didn't quite get it. Yeah. So in your phase yeah. So this holds nicely for a randomly interspersed thing.
So okay, I can give you a setup. So you have high density of.
Transfer all the blues to one side.
Yeah.
Right. So let us say.
If you take a gradient, I guess.
Or something which
just a
has
sharp
some.
discontinuity.
Right.
So if you have a gradient in oscillator density, let us say, then of course traveling waves would more likely occur, because, for example, this phase is because the density of oscillators is low, right? The clustered oscillation.
Right.
Of course, the diffusive coupling is also not very high.
Correct.
But I'm saying, let's take somewhere here, in this region, let us say. You have this much density of oscillators, but if you localize them in one region, now that would be able to excite
Exactly.
the cells.
That is what I'm saying. So
Right?
this holds for randomly.
Correct.
dispersed.
Right.
Yeah. So actually, you might be able to even impose patterns if
Sure.
you put it.
So in fact, that's the paper that Riya, Shakti and I wrote about, like if you have all the
Guys on
cells at
one side.
end
I know you used to know
then
this stuff
gradually
really
you make
well.
a gradient, how does the dynamics
Okay.
change that?
Okay.
Chitabra, how feasible is that?
Which one?
Having a localized pacemaker.
So it depends on the system. So, like for example, if you look at the heart, the sinus node is kind of like that. But the uterus, we were speculating, it's more like a gradient.
Okay.
So,
I have a question as well. Could you show me your mechanical oscillator, the mechanical activity? So what you're claiming is tantamount to having more oscillators. Isn't that correct?
Right.
Right? So, I mean, how you assume harmonic mechanical? What is there a...
So the model is linear elastic solid. The the matrix. Meaning the stress tensor goes proportional to the strain. That's the model I use, so sigma. So if you look at the constitutive relation between sigma and strain, it's linear.
But even, do you still require some oscillators, or just with this in conjunction with excitable units,
Right,
with a
that's-
mismatch in the parameters, still excitable, couldn't you generate traveling waves because of the mechanical this thing? Depending on the shape of the null lines?
Just because of, well, by the way, this is sort of a tissue model, the mechanics. We're looking at the continuum.
Right.
But if your question is even without diffusion coupling between
No,
the
I
cells,
didn't say. I said you have a composition of oscillator and excitable units, correct? If I had just all excitable units in conjunction with your mechanical oscillation, with the heterogeneity in the excitability, shouldn't you be able to
no, so, but then you need-
propagate traveling waves?
but you need a trigger, right? Excitable cells, they do not
That's
get
the
excited
fluctuation
by.
in the null lines. They are not the same parameter value. Excitable yet heterogeneity. I'm just speculating.
Oh,
And you're providing them with mechanical energy.
I mean, if
It's interesting, because if you look at the phase diagram,
Yeah.
we've been having this debate all along, right? That if you put rho equal to 0, would you still get, so if you just go to the phase diagram, you remember with mechanics,
Yeah,
it seems
exactly.
like rho equal to 0.
Exactly.
that is
Exactly. Yeah.
so, okay,
Well, the next one.
right.
Yeah. Yeah. Here, for example, you have traveling waves even with rho equal to 0. It seems like.
Seems like. So that would be very cool. I just think it's very cool. So you're inducing traveling waves in excitable element.
Solly and I have been having this debate for a long time.
I just added entropy to that.
But by the way, I mean, it depends on the resolution that we are looking at. So if
I'm not doubting you.
yeah.
Soling is very careful, very cautious.
See, your thing is you're using the same parameter value in excitability. Excitability is also a domain, right? There are range of parameters in which you shall say excitability. It should not value of in the system domain. What I'm saying is add heterogeneity. I mean, how feasible it is to have all the excitable units at the same level of excitability. Right? Heterogeneity is reality in life, right?
Yeah.
Mimic that, put this simulation that I'm not going to bet anything. Let's Siddhartha bet his PhD. I think you're going to see traveling waves.
Yeah.
Only if you want to try it.
Sure. Yeah.
I have curiosity. What is the practical significance of all this with respect to, say, medical treatment for the heart? Or
I mean, we do our best to make sure that our results have some sort of clinical relevance, but okay. At least the basic principle that mechanics sort of enhances synchronization, that should still hold. But if you want to make the work of clinical relevance, then this simplistic models, Fizio-Nagumo, it's a bit risky. You have to go into a very detailed models where you model each ion channel and then make sure that the parameters are at the right biophysical setting, this and that. Because there has been mistakes where using simple models trying to predict something has cost lives, especially in the study of cardiac arrhythmias. So, yeah.
So again, Soling is very cautious. I'm never that cautious. Even there are doctors in cautious. So I usually stick my neck out and say,
This is almost
Go to
Hodgkin
with
Huxley.
cardiac trouble.
It's a poor man's Hodgkin Huxley. I mean, that won the Nobel Prize, right? Christopher, who was a poor man's Hodgkin Huxley?
No, so one of the things that one can see from this is for example, one of the big mysteries is how does the uterus coordinate its contraction just before the child is born, right? So people, if you ask an obstetrician, just say hormones. But the thing is that if you dissolve all the gap junctions and inject it with as much hormone as you can, there won't be any contraction. So clearly there's a lot of role that the coupling plays. What this is saying is that also the mechanical deformation that the uterus undergoes as the child is trying to push its way through is also helping coordinate the synchronization even further. that is a new angle that this work is bringing.
So enhancing synchronization
Exactly.
via mechanics. That's what, exactly.
Yeah,
That's pretty
it's
cool.
giving you another channel
Yeah,
for
the way-
coupling
yeah,
in some
yeah,
sense, yeah. Which is a
It's
bit
the
longer.
other way
range.
around. Instead of mechanics being synchronized, mechanics cause synchronization.
Because it's giving
I
a
think it's
slightly
pretty
longer
cool.
range coupling, right? With
Right,
it. So
absolutely.
basically, that's
Yeah.
Because it's always been like a big mystery, like what exactly is causing this very quick transition to one input contraction. Like it takes about an hour effectively for the influence to kind of contact as a one entity. So what is causing this switchover? Like gap junction expression is not that fast. So there was just something else. So mechanics might be that missing link.
So, no more questions, let us thanks.
Very nice.
Next we move on to the talk by Santhanam. So, the title will be Transport and Extreme Events of Complex.
This Sudeshna's talk after a gap of an hour. Yeah, this session is the last one.
Does this work?
Just check.
Okay. Okay. Yeah, first let me thank Sitabra for this invitation in honor of Sudeshna. So I chose to talk about extreme events, and if I have time, maybe at the end, a little bit about transport, which is non-random. And I chose extreme events for the reason that in recent times, Sudeshna has also been involved in such extremist activities.
Put that on Facebook.
No, they are recording, you should tell him. So yeah, of course, that's one of the reasons. And anyway, so what I'll do is maybe let me start in some sense from the beginning. So this is in some sense the beginning for me, not for her. So when I joined Professor Vijay Shore as a PhD student in PRL, that was little after this paper was published. And one of the first papers he gave me, he gave me several things to read. This was one of them. Okay. So this was one of the papers that I have. So when I was reading this paper, or when I got this paper, I didn't know who was Sudeshna. Of course, later I got to meet her at PRL itself over many nonlinear dynamics conferences that used to happen there at that time. So I'm not going to explain this paper, but essentially it's about studying some energy eigenvalues under certain symmetry decompositions. And in a lot of quantum chaos, one of the sort of important preoccupation is to study the statistics of these energy levels. Okay? That's a very important quantifier of quantum chaos and so on. And it turned out that many years later, when I started doing work related to extreme events, that was the inspiration. How energy levels are placed on the energy axis for a quantized chaotic system. Okay? And let me explain that part here. Okay? So let's say that this is your energy axis, and here is how. So you can imagine that there is some chaotic system which has been quantized, and these are the placements of energy levels. And the distance between any two of these successive levels is called a level spacing. Now, if I somehow want to retrofit an extreme event study onto this, it's going to be very difficult, because if I simply replace energy by time along this axis, it's not going to work, because typically when you look at a time series or a process, you generally sample it at equal intervals. So it should have been sampled like this at equal intervals, but along the energy axis, I have only these blue guys. So I don't have these other things. Okay, so it doesn't work in a very straightforward manner. On the other hand, if you imagine that each of these blue line here is actually representative of an extreme event, and you're not so much interested in these non-extreme events, like it's sampled at regular intervals, but you're not interested in these things. And what I want to study is actually this time interval between successive occurrence of an extreme event, then you're back in business in some sense. So what would have been called a level spacing statistics in the context of quantum chaos is what is called the return interval distribution, or a similar recurrence interval in the context of extreme events. So here is the setting. So here I have some process as a function of time, and whenever I put in some threshold, and every time I have a crossing above this threshold, I call it an extreme event, and you can convert it into a distribution like this, and all these extreme events would fall in the tail of the distribution. So you're asking the question, what can I say about the events that are there in the tail of the distribution? And typically there are many questions that you can ask about such events. The first is the distribution of extreme events itself. Just asking the question like, how are these numbers distributed? Okay. And that's an extremely old sort of theory. Classical extreme value theory, especially for uncorrelated processes, gives you all universality results. So I'm not going to even describe them. There are like Gumbel and many other distributions. So the other interesting question is, what is the distribution of the return intervals? And again, for uncorrelated processes, it's a fairly easy question to answer. But if your process is correlated, then it's still an outstanding problem. You don't know what is the exact distribution of return intervals for a correlated process. And the third one, which I'll probably speak in the context of networks, is the probability for the occurrence of extreme events. So these are the major ones, but of course you can list many other sort of other things as well. Okay, to set the sort of the background, so a short memory process would be something very close to an uncorrelated process for me, even if not delta correlated. If you have a correlation function that's decaying exponentially, then it's very nice. It's easy to handle because you don't need to remember where it started from. It would have forgotten over a very short exponential time scale. Okay? And in that case, it turns out that the return interval distribution is also exponentially distributed. On the other hand, the difficult ones are these ones which would show long memory, okay? Or typically you would say that it's a complex system if it actually falls in this class. So the autocorrelation decays very slowly, almost something like this. So it's a power law of this type, especially where this exponent gamma lies between 0 and 1. So these are in some sense easy to model, nice ones. These are nightmare in some sense. Unfortunately, most of the natural processes actually fall in this class. They have long memory. So pretty much you can take any natural process or even technological, social, whatever, like atmospheric variables, the kind that Neelima was describing in the morning, pretty much any of the physiological processes, stock market data, earthquakes, whatever, they all fall in this regime. So if for any of these you ask the question about recurrence interval, it's a difficult question to answer. For example, you know that maybe earthquake happened somewhere at this time. When is it likely to happen again? Not an easy question to answer. Because the mean of this time diverges. So there is no typical time scale associated with that. Okay, so these are some examples of such recurrence time distributions coming from solar flares. This is the one coming from earthquakes and so on. So these kind of results were known from many different areas of this kind. So typically what happens is you see something like this is actually more closer to a stretched exponential, and closer to small return interval values you see something like that looks like a straight line in this log-log plot, more like a power law. And you can do that for even some nice things, like for instance you can take a huge amount of text and ask for return of a particular word, and that also turns out to be a product of these two factors. Now let me go back to what I was saying initially about how energy levels are placed on the energy axis vis-a-vis the extreme events on time axis. Okay, so we used a similar analogy. So in the random matrix theory, where all these ideas originated, it would be called Wigner surmise. And applying that straight away requires quite a bit of changing the basic parameters and stuff like that. So I'm not going to show you the full derivation, but actually we were able to obtain this expression as the return recurrence time distribution. And so this gamma is the autocorrelation exponent that you saw here, this one. So in other words, your recurrence time distribution is characterized by this relation, where you can see gammas all over the place. So there are no other parameters. Now, what does this tell me? So if you look at it, this is a constant, simply a number, whatever it is, but there are two parts to it. So for small values of return interval, it is dominated by a power law of this form. And for large values, it is dominated by a stretched exponential. So in other words, again, going back to the so-called Wigner surmise, what you do is typically, I have a energy level here. If I want to know where is the next one that's going to happen, so it's basically a product of probability that over some interval you don't have an energy level, and a probability that over a small interval after that there will be one energy level. Okay. A very similar kind of argument goes into obtaining this relation. And very nicely, if you put gamma equal to 1, you actually go back to the uncorrelated process, and it also gives you reduces to simply e power minus r. Okay. And of course, for large values of r, this term dominates, and for small values of r, this term dominates. So essentially, starting from where I began with all these quantum chaos setting, you could get some very useful formula for the recurrence distribution of extreme events for a univariate time series. And here is the proof of the pudding, in a sense. So these circles that you see are the numerical simulations, and for different values of gamma. So gamma being close to 1 is it's a lot more correlated, a worst case scenario, compared to gamma being close to 1 means it's nearly uncorrelated. So you see a very nice a reasonable agreement. And we also checked it with one kind of data that I had at that time. It's a measured wind data, which had a gamma of about 0.24. Blue line is simply the plot of the expression that I have. Okay. So this is one part that I wanted to discuss. The second is, again, going back to the scenario of extreme events. You could ask the question, what if these events are actually happening on a network? What can I say about such a case? So here, let me explain the basic scenario. So here I have a network. I don't need to explain what a network is, and there are random walkers on that network. So you can imagine, like, you have a network, and there are, to fix your mind on it, you can imagine that there are packets of information flowing on the network, or maybe something like vehicles on highways and so on. And extreme event is based on the number of walkers in a given node on the network. So for example, let's say at some time it should have been t equal to 0. At some time t equal to 0, this is a small snapshot of a network, and there are these blue circles which are your walkers. And at some other time, suddenly 4 of those walkers find themselves on the same node. That would be an extreme event, possibly. And these kinds of events happen due to natural inherent fluctuations. Okay? So there are no external shocks which are inducing the occurrence of these events. It happens on its own. So then you want to ask, what is the probability that such events happen? And it turns out that this is an exactly solvable problem. So I'll not do the full derivation, but essentially we are looking at any network with n nodes. There are total number of k edges and w non-interacting walkers. And so here you can go through the entire derivation, but essentially the important element here is that you identify a threshold. What kind of threshold should one identify? Typically it is taken as the mean flux that's passing through that particular node. So I here is the subscript for that particular node in question. So it's the mean flux plus some standard deviation, and you can choose this q. So you could put q equal to 4 and say I'm looking at events which are 4 sigma or larger. That would be the sense of extreme events for you. So you can do that and actually do all the calculations, and finally you can write the probability for the occurrence of extreme events. And as you can see, the whole the probability depends only on the degree of the node in question. And so this turns out to be one of those special functions. Let me, an incomplete beta function, but I'll not get into it. I'll show you the graph. Okay. It depends only on the degree of the ith node in questions. And this is how the result looks like. So for example, you look at this top panel here, the blue dots are the simulation results, and the continuous line is the analytical result. So what you notice is that, so here is the region of small degree nodes, and the probability for occurrence of extreme event is larger for the small degree nodes, but it is actually much smaller for the high degree nodes. This is not what you would expect. Hubs by definition actually attract more walkers. So a large number of flux passes through the hubs, and typically you would expect that those would be the hotspots in a network. Turns out that that is not really the case when you use this kind of a threshold, which weighs the threshold as per the mean flux, typical flux that is passing through the network.
So hubs have larger mean, right?
Hubs have larger mean. Yeah, that's right. But less, yeah, that's right. Yeah. So the central result is that the small degree nodes like these are more likely to encounter extreme events as compared to the hubs of the network. And now you can actually relax many conditions. For instance, okay, at least for this simulation we chose q equal to 4, meaning 4 sigma events and above, but you can choose any number you want. Or you can relax the condition that the total number of walkers is a constant on the network. So you can relax many conditions, but the central result remains the same. And actually you can relax many more things. So for instance, the model that I just described here, I called it a conservative model for the reason that the total number of walkers is a constant throughout the simulation, and it's a standard random walk generalized to a network scenario. On the other hand, you can construct a so-called non-equilibrium model where many things will be changing. For instance, you start with 0 walkers, but at every node there is a probability for the birth of walkers. There is a probability for a walker to be absorbed at that point, or you can actually in principle attach these buffers. So essentially they are queues created at each of these nodes, and they have variable size. So if the queue is full, this node will not be able to admit any more walker. So it will have to reject. So there is a rejection probability as well. So you can construct a more detailed model with all these things taken into account. And maybe before I tell you what happens there, let me say that at least for the conservative model, many results are known. Many are exactly known, like the occupation probability, the kind of thing that you said, depends on Ki. So larger the hub, which has higher degree, will also attract more walkers. First passage time is known. Many other quantities are exactly known. Whereas in the case of non-equilibrium model, most of these are not known exactly. But what it gives rise to is two different kinds of possibilities. One, you can have a free flow state, meaning that there is walkers are moving on the network. So you remember that you have these buffers. So it is possible that buffers are full everywhere and you are in a congested state. So the number of walkers is increasing on the network, so you come to a sort of standstill. Network is dysfunctional. So in principle, what you can have is a transition from a free flow to a congested state, depending on the birth probability. Okay, and in fact, it happens depending on many other parameters as well. But this is a very useful parameter to track this transition from a free flow to a congested state, often called the jamming transition. Okay. So the order parameter is roughly the total number of walkers or the rate of change of number of walkers in the network. So here it turns out that if you are in the free flow state, which means that you are in a regime like this, so here it's the total number of walkers as a function of time, then again the extreme event properties are same as for the conservative model. On the other hand, you can't really define even an extreme event here because it's already something where the number of walkers is increasing with time. Okay, so even in a non-equilibrium model, the result of an equilibrium model actually works well, especially this central property that small degree nodes have more chance of extreme events. Now, you can ask the question for the edges of the networks. So now that you've seen what it means to have extreme events on the nodes of a network, you can say that, let's say there is a walker here on the ith node at time t minus 1, and at time t, this walker moves from here to here, following this edge. Then you could say that at time t, the walker was actually on this edge, and you can label this edge as Eij. So now you can turn around the question and ask what is the probability of extreme events happening on the edges of the network. Naively thinking about it, one might imagine that it's all the same problem, why do it all over again? But it turns out that nodes and edges are not interchangeable. So you can't convert all nodes into edges and edges into nodes and hope that the answer would remain the same. It is not. And secondly, the dynamics and especially the extreme event dynamics on nodes and on the edges, they are very different, they are uncorrelated, which is what I'll try and show in the next few slides. So we can define two kinds of quantities, load and flux. So let's say that at some particular time here, t minus 1, there are ni walkers and nj walkers on these two nodes. Now at time t, a part of these walkers are actually jumping through this edge and reaching here. And similarly, a part of this nj walkers, which is lj, actually are jumping using this edge and reaching here. Now then your load is simply the sum of this Li and Lj, and flux is the difference between Li and Lj. So now you can go back and ask, are there extremes in this load and flux? Again, it turns out that this is also an exactly solvable problem. So I'm not going to do the derivation here. You end up with another special function and so on. But the interesting thing is that the probability for the occurrence of the extreme events in load does not depend on the degree. For the entire network, it's actually a constant. So you can see that it's a constant for a given value of q. the given value of the threshold for extreme events that you set. Okay, so it's very different from what we saw for a node on the network. And especially, so that is something different. And you can also ask the question, suppose let's say I have a snapshot of a network like this. At time t, there is an extreme event here at this point, shown in red. Now at time t plus 1, there is a possibility that one of these three edges will experience an extreme event, one or all three maybe, or any two and so on. So the question is, can I see if there are any correlations between extreme events happening on a node and on the edges that are being connected? So that's the thing. Are there correlations between extreme events on the nodes and edges? It turns out that the correlation is very, very minor. So you can see that the number is about 0.1 at max for a time lag of 1. Okay? So in other words, if there is an extreme event here, one time step later, there is a 10% chance that one of these might have an extreme event. And in fact, generally it is much lower. So in spite of all the randomness, there is a measurable correlation, but it is extremely weak. So you will see that in this plot. So you can see that the maximum correlation that you see here is in yellow, which is of the order of about 0.05 or thereabouts. Okay. So in other words, another way of restating that is to say that the extreme events and nodes and edges are very different kind of beasts. They need to be studied separately. In particular, especially for random networks with random walkers, an event in one does not imply that there will be event in the other, meaning that extreme events in nodes does not imply that there will be extreme events in the edges. Okay, so I seem to have 10 more minutes. So let me do this last part where transport is involved, but there is no randomness. There is network, but not really a random network. Okay, so this actually the background to this is that around early 2020 when the pandemic hit, so we started looking at me and two of my colleagues, Srijit and Sachin Jain. So we started looking at, is there something that we can contribute? So let me explain to you what we did. So the motivation was this. So this goes back to after the so-called Spanish flu, after the First World War. So there was this sanitary inspector's report to the government of India, which you can easily access. Basically, it says that the railways played a prominent part, as was inevitable, in actually spreading the infection. A large number of people died due to Spanish flu, by the way. Even apparently Mahatma Gandhi had a little bit of that. He had lifelong weakness because of that, it seems. Anyway, so during the panic caused by the epidemic, trains were filled with immigrants from infected centers, many of them being ill, and so on. And it says the second epidemic was carried from province to province, and place to place within each province by travelers by train, river boats, and so on. And so in fact, the so-called popular SIR model, when it was first published, actually drew data from Bombay itself. So this is the first paper that was published on this so-called compartmental models by Kermack and McKendrick. And this is exactly the figure that's there in this paper, which drew from the plague data in Bombay between 1905 and 1907. Okay, so this is number of deaths as a function of weeks. So the question that we asked was the following. That is, the basic premise is, whatever be the severity of your infectious disease, okay, the spread itself is caused by mobility of people. No, it could be weak or a stronger infection, but the spreading is caused by the mobility of people, especially due to transportation networks. So then you can pose a question like this. If I have a network of n cities or towns, x1 up to xn, and if one of those places, let's say x1 is declared to be an outbreak location, can a hazard value be assigned to all other cities, reflecting the risk of catching the infection? So this is not about predicting the case loads. Okay? So it's like you have a network and you need to look at the transport of infection or diffusion of infection from what is determined to be or given to be a outbreak location based on the statement of the problem. And okay, so I'm going to, in view of time, I'll cut the whole thing short. So this, so here the typical compartmental models have several compartments. So the standard SIR model has S, I, and R for susceptible, infected, and recovered populations. Okay, so these are the three sets of equation within this blue curve that you see here, and that's the standard SIR model. So there are these two parameters, alpha and beta for various rates, susceptible and recovered rates. Now, if you have to somehow add to this model information about the mobility, you need to take into account the moment kinetics, which actually comes from this part of the equation, okay, where these F encapsulates the probability of people going from city M to city N. So M and N are going from 1 to capital M. That's the number of cities or towns in your network. So as I said, I'm not going to describe this whole thing fully. This is basically what we have added to the SIR model. So essentially it's augmenting SIR model with mobility. Now, and we basically, now this part is one thing, but to be able to evaluate this numerically, we didn't want to do it as a synthetic model with synthetic data, so we took the real data. So we considered a large number of cities and towns in India, about 450 of them, all of them above 1 lakh population. So that comes from the census data, and then we took the real mobility data of train, road, and air transport. So at least for train and air transport, the data is easily available. You can scrape it off the web. Road is a little more difficult, and in some places we had to supplement it with with our own model. So this whole thing provides us the mobility augmentation, and finally you calculate something called effective distance and time of arrival. So this is what the whole thing looks like. So you choose 446 cities and towns in India with a population of 1 lakh or more. You use the real available data for train, air, and road traffic. And we, of course, discarded all the local mobility, all the local trains in Chennai, local trains in Bombay. That traffic is quite a bit. So since we are interested at a larger scale spread of infection, we are not interested in those local passenger train data. So here is the summary of all that we could assemble. So for example, if you look at the last line here, it turns out that, of course, not very surprisingly, railways actually carry 73% of the passengers, and air travel is about 6% and 21% by roads. As far as this network goes, this network that you see here is made up of 446 nodes, and there are 46,448 edges. Okay, so how do we figure out the arrival of infection? So what you find is that now you run the model with all the data and everything, and the time of arrival at any particular city is taken to be at least 10 infections. If there are at least 10 infections in that city, you assume that, you say that the infection has arrived. And before anything, you will have to first decide what is your outbreak location with a certain number of initial infection. So you plant it in some place like Bombay or wherever that you want to, and start off your simulation. And now you also have the geographical distance between various places. all these places. Now if you plot the geographical distance as a function of time of arrival between all these 446 cities. So this, for example, in this simulation, the outbreak location has been taken to be Delhi. So you planned some 20 or 30 infections there, and then use the real mobility data and everything and run the thing. So you see that there is no correlation at all between the geographical distance and the time of arrival. On the other hand, you have an effective distance which combines not only the geographical distance, but more importantly, the mobility data. Like if there are two places in the country where hardly anyone goes, then they are really not separated as far as infections. They are very well separated as far as infection is concerned. But two places where they may be very far, but if there is too much traffic between them, then they are very closer. That's the kind of information that this effective distance actually captures. So you see that there is a very nice correlation between time of arrival and the effective distance. So you can choose any city. This is a small town, Tirupati, not far from Chennai. So you get a similar sort of correlation.
The effective is subjective.
No, it's not subjective.
How did you calculate that?
Okay, so
If I may.
yeah, okay, so I think I removed that slide, but it's actually based on the probabilities of people going from one place to another. It's based on those F that I had shown there. Okay. So it's not subjective, yeah. Okay, so just to show you the thing, now you can rank it depending on time of arrival, because your time of arrival is linearly proportional to this. So for example, let me show you this. For instance, let's say that Tirupati and Bombay are two cities that you assume to be outbreak locations. Now Tirupati and Bangalore are very close. So if there is an outbreak at Tirupati, it takes, this data says that it takes 5 days to reach Mumbai. On the other hand, if the outbreak location is Mumbai, 5 days to reach Bangalore, and whereas if it is Mumbai, it takes only 2.5 days to reach Bangalore, simply because even though they are far away from one another, it's just that the mobility is quite a lot between here and here. And this actually has a nice web resource. You can go there and see, and in this here you can actually choose any of these 446 cities as a outbreak location, and immediately it shows you the hazard map for every other city in the country. So you can try it out on your own whenever you get time. You can also see many other statistics in that website.
Sorry if I missed this, but is it they are not symmetrical in that if there's an outbreak in Chennai, is it as with Tirupati as?
No, it is not. It is not symmetrical. Yeah. Okay, and also it agrees. So unfortunately there was a second wave, and for us, of course, it was data, like it or not. So we were able to compare these arrival times, because from the second wave onwards, roughly we were able to track it much better. And out of those 12 cities, at least 10 of them did figure in the top 10. So I would say like there was about 80 to 85% agreement there. Okay, I'm going to stop here with this brief summary that transport and extreme events are very, very interesting, especially on networks. They display very interesting properties, and something that I really did not speak about is that you can simply only look at extreme events and figure out most of the other properties of the system. In other words, it's a gateway to studying the entire system itself. Okay? So in that sense, extreme events are very important. And over the years, many students have worked on this, and of course my colleagues Srijit and Sachin Jain. So I'll stop here with this and welcome questions if you have.
It's going to be a very stupid question, nonetheless. This is the last question of the day, perhaps. So, see, usually when you were talking about extreme events, right, you said natural things with, stochastic component. Would something on the lines of Shinlikov chaos also fall into them, because Lyapunov exponent between one spike and the other is so much that once you get a big spike and then you go around the unstable focus for a long time, would that be considered?
Yeah, that would also be,
It's completely deterministic.
Yeah.
Right? Nonetheless, due to the Lyapunov, you've lost correlation
Yeah.
between the first and
Yeah, that would very well fall within this
Okay,
frame.
I was just
Yeah.
Yeah, because Ulrich and
Yeah.
they've
done, yeah, right.
single thing and the homothetical which
Yeah,
goes
yeah,
off,
yeah,
does that.
Yeah.
Silicon, right?
Yeah,
So-
exactly.
Yeah. So there is a body of work where instead of random walkers, they actually put dynamical systems on the network and study extreme events. Yeah.
Equally valid.
Yeah. In fact, I think Sudeshna's.
Difference between
Yeah. In fact, some of her work, is of that types more recently. Yeah.
There is absolutely no way of fingerprinting
it's
one or the
nothing.
other. Ki This is comes from a stochastic source, this comes
No,
from return.
no.
Because the
Yeah.
correlations
No
are not
memory
so
at all.
fast.
No.
But you seem to say you have a long-term memory, long tail.
No, so okay, so I should differentiate. As far as this model is concerned, random walkers on random networks, it is actually memoryless. Whereas the other one where we were looking at a univariate time series down from real process, they have a long memory. Now if I have to induce long memory here, I need a random walk process. Yeah, I need to put some correlation.
Go to zero, it just comes up and so I was
Yeah.
wondering, there is no way you can discriminate between from, I'm just asking you.
No, I mean, if it is aperiodic, rare, all those things, it takes all the boxes.
It takes care of most of it, yeah.
Can we interpret the occurrence of extreme events in the context of intermittency?
Yeah, you can, yeah. Yeah, you can have those regimes of intermittency. You can say that that is extreme. And in fact, the time interval between that shows 1/f noise, which is
So just like type 1, type 2, type 3 intermittency,
Yeah.
can be classified
Yeah,
types of,
certainly,
extreme events?
yeah, correct.
So calling them extreme events is like basically repackaging the problem.
Yeah, that's right. See, it appears in many different avatars in different. Like I was saying, like you can put a camera in a small region for your experiment.
Dragon events.
I know, the same thing.
Yeah.
Dragon
Yeah.
thing.
Exactly.
So, which is why I think it's more common than we actually think. Yeah.
But there is something still nice, because most of the extreme event literature was for uncorrelated, the stuff in all the examples, but here they are perfectly deterministic.
Yeah, that's right.
So that's
Yeah.
very nice, I thought.
Have you looked at directed graphs, directed networks for the first
no,
part
actually,
of the
yeah, it's a good question. No, we have not done that, but that is something where you can do similar analysis. Yeah.
But do you think that the probability occupation result will still hold? It being proportional to the degree
Yeah,
of the...
provided there is stochasticity, yeah, I would expect so.
Provided there is?
Why would there be?
No, provided there is? I didn't
No,
hear you.
provided there is stochasticity. Yeah, there has to be some stochasticity in the problem. Yeah.
But you would think it's proportional to the in degree.
Right. Yeah. In fact, someone else had done not exactly on the electrical networks, but where they don't have these discrete walkers, but a more continuous version of this. And there they see very similar results already.
Santanam, so I had a quick question. So this time-delayed cross-correlation matrix that you spoke about just before you switched on to this Spanish flu thing. So does it now provide some kind of an answer to this long-standing puzzle we had discussed sometimes about, why do the stock market delayed cross-correlation matrix show like significant signals even 2 or 3 days later when we know that the autocorrelation decays very quickly? Can that provide some kind of answer to that?
Okay. Okay. Frankly speaking, I don't know because because this is also really, especially if you're looking at the returns, which is what is interesting there. You do see the kind of effect there as you do see that effect that you just described. You do see at least for 2 to 3 days you do see that. Yeah. So that's like saying that there is some amount of correlation, residual correlation that can be actually used.
But the funny part is the autocorrelation decays within minutes.
Yeah, that's right.
But
same thing here as
but
well.
the delayed cross-correlation lasts for days.
Exactly. So even here, because it's all random walkers, the autocorrelation decays more or less instantaneously. Yeah.
So would you suggest that this could be the mechanism by which it's...
Okay, I have not thought about it in that
Okay.
context, but maybe, yeah.
Okay, thank you.
Thanks, Professor Jagannathan. So that brings us to an end, the post-lunch session. So the remaining event is, of course, Professor Ashwideshna Sinha's colloquium talk, which has been also announced as IMSC Diamond Jubilee Colloquium. So that's going to take place in the auditorium, which is downstairs, and tea has been arranged kind of. They told me it's high tea. I don't know what that high part corresponds to. It's very confusing. That's from 4:15. So, but before ending, I have this privilege of thanking the various people who have been involved. You know, it's almost like this is the end of the thing, but you know, because I'm pretty sure no one will stick around after your Diamond Jubilee colloquium. I'll let.
It's plenty.
Right. So let me thank all the various people who have been involved, and certainly the office of the institute has been extremely proactive in making sure that all the arrangements have happened. In particular, our extremely dynamic administrative officer, Srimati Indra. She's been like on this for ever since we had thought of this plan. She had been working on this along with a team. So I'd definitely like to thank Srimati Indra and the entire IMSC office